Let's go through the full algebra breakdown for all 5 questions, showing every single term's differentiation, not just the final answers. Question 1. The gradient. Take f equals x squared z plus 3xy minus y squared z. First, we find partial f by partial x, freezing y and z since they're treated as constants. Term by term, partial of x squared z with respect to x is held constant, and x squared differentiates to 2x, so this term gives 2xz. Partial of 3xy with respect to x, y is held constant, and x differentiates to 1, so this term gives 3y. Partial of negative y squared z with respect to x, there's no x in this term at all, so it vanishes to 0. Adding these 3 results, partial f by partial x equals 2xz plus 3y. Next, partial f by partial y, freezing x and z. Partial of x squared z with respect to y. There's no y here, so it vanishes to 0. Partial of 3xy with respect to y, x is held constant, and y differentiates to 1, giving 3x. Partial of negative y squared z with respect to y, z is held constant, and y squared differentiates to 2y, giving negative 2yz. Adding these, partial f by partial y equals 3x minus 2yz. Next, partial f by partial z, freezing x and y. Partial of x squared z with respect to z. X squared is held constant, and z differentiates to 1, giving x squared. Partial of 3xy with respect to z. There's no z here, so it vanishes to 0. Partial of negative y squared z with respect to z. Y squared is held constant, and z differentiates to 1, giving negative y squared. Adding these, partial f by partial z equals x squared minus y squared. Now assemble the full vector. Gradient of f equals the quantity 2xz plus 3y I hat plus the quantity 3x minus 2yz j hat plus the quantity x squared minus y squared k hat. Question 2. Curl. Take f equals yz I hat plus xz j hat plus xy k hat, so p equals yz, q equals xz, and r equals xy. For the I component, we need partial of r with respect to y minus partial of q with respect to z. Partial of r, which is xy with respect to y. X is held constant. Y differentiates to 1, giving x. Partial of q, which is xz with respect to z. X is held constant. Z differentiates to 1, giving x. Subtracting x minus x equals 0. For the j component, we need negative of partial of r with respect to x minus partial of p with respect to z. Partial of r with respect to x. Y is held constant, giving y. Partial of p, which is yz, with respect to z. Y is held constant, giving y. Inside the bracket, y minus y equals 0, and applying the negative sign still gives 0. For the k component, we need partial of q with respect to x minus partial of p with respect to y. Partial of q, which is xz, with respect to x, z is held constant, giving z. Partial of p, which is yz, with respect to y, z is held constant, giving z. Subtracting, z minus z equals 0, so curl of f equals 0, I hat plus 0, j hat plus 0, k hat, the 0 vector. Question 3. Divergence. Take f equals x squared y I hat minus 2yz j hat plus xz squared k hat, so p equals x squared y, q equals negative 2yz, and r equals xz squared. Partial of p with respect to x. Y is held constant, and x squared differentiates to 2x, giving 2xy. Partial of q with respect to y. Z is held constant, y differentiates to 1, multiplied by negative 2, giving negative 2z. Partial of r with respect to z. X is held constant, and z squared differentiates to 2z, giving 2xz. Adding all 3, divergence of f equals 2xy minus 2z plus 2xz. Question 4. Testing for conservative, then building the potential function with full reasoning. Take f equals the quantity 2xy plus z cubed I hat plus the quantity x squared plus 2yz j hat plus the quantity 3xz squared plus y squared k hat. So p equals 2xy plus z cubed, q equals x squared plus 2yz, and r equals 3xz squared plus y squared. Part A, the curl test. For the I component, partial of r with respect to y, the 3xz squared part has no y, so it vanishes, and y squared differentiates to 2y, giving 2y. Partial of q with respect to z, the x squared part has no z, so it vanishes, and 2yz differentiates to 2y, giving 2y. Subtracting 2y minus 2y equals 0. For the j component, partial of r with respect to x, the y squared part has no x, so it vanishes, and 3xz squared differentiates to 3z squared. Partial of p with respect to z, the 2xy part has no z, so it vanishes, and z cubed differentiates to 3z squared. Inside the bracket, 3z squared minus 3z squared equals 0, and negated, it is still 0. For the k component, partial of q with respect to x, the 2yz part has no x, so it vanishes, and x squared differentiates to 2x. Partial of p with respect to y, the z cubed part has no y, so it vanishes, and 2xy differentiates to 2x. Subtracting 2x minus 2x equals 0, so curl of f is 0, which means f is conservative. Part B, building the potential function f, one equation at a time. First partial f by partial x equals p, which is 2xy plus z cubed. Integrating with respect to x, treating y and z as constants, gives f equals x squared y plus xz cubed plus some unknown function of I and z. Call this equation 1. Second, partial f by partial y equals q, which is x squared plus 2yz. Integrating with respect to y, treating x and z as constants, gives f equals x squared y plus y squared z plus some unknown function of x and z. Call this equation 2. Third, partial f by partial z equals r, which is 3xz squared plus y squared. Integrating with respect to z, treating x and y as constants, gives f equals xz cubed plus y squared z plus some unknown function of x and y. Call this equation 3. Now compare all three equations term by term. Every distinct term that shows up in any one equation has to show up in the final answer. Collecting across all three, x squared y appears in equations 1 and 2, xz cubed appears in equations 1 and 3, and y squared z appears in equations 2 and 3. This tells us the unknown function in equation 1 must be y squared z, the unknown function in equation 2 must be xz cubed, and the unknown function in equation 3 must be x squared y. Putting it all together, the final potential function is f equals x squared y plus xz cubed plus y squared z, and we could add any constant here too, since constants always vanish under differentiation. Question 5, proving no vector field exists. Take f equals xy I hat plus y squared z j hat plus 3xz k hat. So p equals xy, q equals y squared z, and r equals 3xz. Partial of p with respect to x, y is held constant and x differentiates to 1, giving y. Partial of q with respect to y, z is held constant and y squared differentiates to 2y, giving 2yz. Partial of r with respect to z, x is held constant, z differentiates to 1 multiplied by 3, giving 3x. Adding all three, divergence of f equals y plus 2yz plus 3x. To check whether this is identically 0, try plugging in some numbers. Let x, y, and z all equal 1. That gives 1 plus 2 plus 3, which is 6, not 0. So the divergence of f is not identically 0. Now apply the theorem. If some vector field G existed such that curl of G equals f, then divergence of f would have to equal divergence of curl of G, which is always 0. Since divergence of f is not 0, no such G can exist.